Welcome back to the deep dive. We're here to, crack open those big ideas so you walk away well-informed and maybe, just maybe, a little surprised. Today we're diving into something really fundamental. It's about how we understand and how we trust scientific discovery. Have you ever stopped and wondered why, with all the brilliant minds out there, all the rigorous methods, why some scientific results just don't seem to hold up when someone else tries them? Well, it's often not just about simple errors. There seems to be a deeper, more systemic thing going on. So our mission today is to uncover this surprising challenge that's kind of built right into the structure of science itself. We're talking about the problem of reproducibility. And we're getting to the heart of it using Remco Heesen's really insightful paper, Expediting the Flow of Knowledge versus Rushing into Print. This deep dive hopefully will shine a light on those hidden pressures scientists face, pressures that can sometimes push them to prioritize, speed and impact, maybe at the expense of results that could be reliably reproduced.
Exactly. And for you, our listener, understanding these systemic issues isn't about losing trust in science. Actually, it's quite the opposite. It's about building a more, let's say, nuanced, a more sophisticated understanding of how scientific knowledge is really generated, how it's validated, and yes, sometimes how it can sort of go astray. This perspective, I think, helps all of us evaluate information more critically and appreciate the true complexities behind discovery.
Okay, so let's unpack this. We hear these terms thrown around, sometimes whispers, sometimes shouts, about a reproducibility crisis in science. But hang on, before we jump into the whole crisis aspect, what exactly is reproducibility in science? What are we talking about?
Right. At its core, reproducibility is it's the expectation that if someone else, anyone competent, performs the same experiment again, anywhere, anytime, they should get basically the same result, or at least, a statistically similar one. It's absolutely fundamental, a cornerstone of the scientific method, really, because it's how we figure out general laws, general principles. Think about it. If a finding only works for one specific person under very unique conditions, it doesn't really add much to our general understanding of how the world works, does it?
No, it has to be universal in a sense.
Exactly. It's about making sure findings aren't just tied to someone's, special knack or a single moment in time, but reflect something more universal.
And this isn't just some abstract philosophical debate, is it? I mean, there's actual evidence that sparked these concerns. I remember reading back in 2011, researchers like Prince noted this general impression that many published results are hard to reproduce. And it wasn't just an impression. You had pharmaceutical companies, for example, who were usually incredibly thorough. They found they could reproduce less than a quarter of key results in cancer biology research. Less than a quarter.
Yeah, imagine that if you're trying to develop new drugs based on that research, that's a massive, massive roadblock, a huge waste of resources, potentially.
And then things got even more systematic, didn't they? These big studies started coming out. One looked at prominent psychology journals, found less than half the results could be successfully reproduced. Less than half. And in social science, another big study found it was just slightly over half.
Right. And these numbers, they're not small potatoes. They definitely point towards a significant challenge in how we, check and validate scientific knowledge.
Okay, but here's where it gets interesting. Because the source material, Heesen's paper, adds a layer of complexity, right?
That's right. What's fascinating here is that Heesen points out, and it's a crucial nuance, that these empirical rates, while concerning, don't automatically prove there's a crisis in the way we might think. We need to consider what reproducibility rates we should expect, given how science works. He uses this toy model from Ioannidis back in 2005. It basically illustrated that if only a really small fraction of projects, let's say 1 in 21, are actually genuine discoveries, and science naturally includes a certain rate of false findings, like a 5% false discovery rate, then finding that only 50% of published results reproduce might actually be perfectly expected, even if science was being done properly, quote unquote.
Yeah. Okay, so the baseline matters. What percentage of research should we expect to be true breakthroughs versus exploration or even false leads?
Precisely. The true number of genuine discoveries out there, plus the inherent error rates in research, significantly influence what our expectations for reproducibility should even be. It complicates the narrative.
So if the stats alone don't definitively prove a crisis, what is the core problem that Heesen identifies? It's not just the numbers then.
Exactly. He zeroes right in on the systemic incentives. It's about the reward structure of science itself.
Ah, okay. The whole credit system in science.
Hmm.
That makes sense. It's a huge driver, isn't it? We're talking about getting recognition for your work, getting published in those big journals, getting cited by other scientists, winning awards, securing grants.
Absolutely. It's central to a scientist's career. Their
Absolutely.
funding, their promotions, their reputation, it all hinges on this. And, people who study science philosophers, sociologists like Hull, Kitcher, Merton, they've recognized this for a long time. It's a powerful motivator.
It is. And it's important to say this credit incentive isn't all bad, right?
Right.
The literature actually points out some positive effects.
Oh, definitely. It's often highlighted for its benefits. It can help optimally distribute scientists across different research topics so we don't all study the same thing. Some argue it speeds up scientific progress overall, which is obviously good for society. It can encourage collaboration, too, scientists working together. And it definitely motivates researchers to share their findings widely, through publication. Knowledge needs to circulate.
Okay, that all sounds pretty good. Driving progress, sharing knowledge. But here's where it gets really interesting. There's the flip side, isn't there? A potential dark side to this credit system that Heesen flags, especially when it comes to reproducibility.
There absolutely is. Heesen argues that these exact same credit incentives can have pretty significant negative consequences, specifically impacting whether findings can be reproduced later on. But he makes a really key distinction. He separates what he terms rushing into print from other well-known issues that also harm reproducibility.
Okay, maybe let's quickly touch on those other issues first, just so we understand the landscape.
Good idea. So first, there's what's called publication bias. This is the tendency for journals to prefer publishing positive result studies that find a significant effect, that reject the null hypothesis.
Right, the exciting findings.
Exactly. And this leads to the famous file drawer problem, where studies showing negative or inconclusive results just get tucked away, unpublished, they don't see the light of day.
Which skews the overall picture of the evidence.
Precisely. Then there's novelty bias. Journals, and funders too, often prefer brand new, groundbreaking results over studies that simply replicate previous work.
Yeah, why publish something that just says, yep, they were right? It's less exciting.
Right, which directly disincentivizes researchers from doing those crucial direct replication studies. And this leads to the third issue, checking bias. If there's a little reward or incentive for scientists to even try and reproduce someone else's work, then the original researchers, well, they have less pressure on them to make absolutely sure their own work is robust and easily reproducible in the first place. The checking mechanism is weakened.
Okay, so those three, publication bias, novelty bias, checking bias, seem interconnected. What are the usual solutions proposed for those?
Well, for those, the solutions seem relatively straightforward conceptually, though maybe hard to implement perfectly. Things like actively publishing and rewarding null results.
Yeah.
And importantly, creating specific tracks or funding mechanisms for replication studies, recognizing their value. It's about balancing the incentives.
Got it. But Heesen argues that rushing into print is fundamentally different from these biases. How so?
He emphasizes that rushing into print isn't really about what type of result gets published, positive, negative, novel replication. It's a more general sort of structural incentive that's tied directly to the credit reward system itself. It's purely about the speed and potential impact of getting your work out there. Sometimes that pressure for speed comes at the direct expense of taking the extra time needed to ensure the work is truly rigorously reproducible. It's a systemic pressure to be fast.
Okay, to really make this concrete, let's dive into that dramatic, real-world example you mentioned earlier. The Fleischmann and Pons cold fusion case. That's quite a story.
Yep.
So set the scene for us. March 23rd, 1989. What happened?
Right. You have these two established chemists, Martin Fleischmann and Stanley Pons, at the University of Utah. They hold a major press conference. Big announcement. They claim they've achieved nuclear fusion, the power source of stars, but at room temperature, using a pretty simple electrolysis setup in their lab. Cold fusion, they called it.
Which sounds impossible based on standard physics, right?
Yeah.
Fusion needs incredibly high temperatures.
Exactly. Conventional physics at the time, and still largely today, requires temperatures over, 100 million degrees for sustained fusion. So this was revolutionary, to say the least. They claim their setup was producing significantly more heat energy than the electrical energy they were putting in, up to 4 times more, they said.
Wow. The implications must have seemed enormous.
Oh, absolutely mind-boggling. Imagine a clean, cheap, virtually limitless energy source. It triggered massive media hype almost instantly. Scientists all over the world were captivated. People dropped what they were doing, rushed to their labs to try and replicate the seemingly miraculous experiment. It was like a scientific gold rush.
But the gold rush didn't last long, did it? What happened next?
No, it fizzled out remarkably quickly. While there were some initial scattered claims of replication, they very quickly came under intense scrutiny and criticism, those crucial excess heat measurements. Many were attributed to experimental errors, like not properly accounting for gases recombining, which also produces heat. Basic mistakes in some cases.
And what about the other evidence, like neutrons? Fusion should produce neutrons.
Right. Their initial claims of detecting neutrons, which would be strong evidence of fusion, couldn't be reproduced by labs using much more sophisticated, sensitive equipment. The signals just weren't there.
So the whole thing just collapsed under scrutiny.
Pretty much. By May 1989, just a couple of months after that huge press conference, the overwhelming scientific consensus had shifted. The phenomenon, as they described it, was deemed irreproducible.
Ouch. The critic must have been harsh.
Unsparing is the word. Authors like Frank Close and John Heisen later called it the scientific fiasco of the century. They basically said Fleischmann and Pons went public too soon with immature results. The damage to their reputations was immense.
Okay, so this brings us right back to Heesen's core argument. Why? Why did Fleischmann and Pons make this decision, this seemingly fateful decision, as Heesen puts it, to go public when apparently they themselves felt they needed more time? They mentioned wanting 18 more months, right?
Exactly. They felt they weren't ready. So why the rush? Heesen points directly to the intense competition, the race for credit. There was another physicist, Stephen Jones, at nearby Brigham Young University, who was working on a very similar project, looking for low-level signs of fusion.
Ah, a competitor.
Precisely. Apparently, Fleischmann and Pons had initially agreed with Jones to submit their papers simultaneously to the journal Nature on March 24th, a coordinated release. But then, just days before that deadline, they abruptly submitted their paper to a different, perhaps faster journal on March 11th. And crucially, they held that press conference on March 23rd, beating Jones to the public announcement.
So they jumped the gun, essentially. Why?
According to Heesen, drawing on sources like Close's account, their explicit goal was to establish priority, to claim the credit before Jones could. Fleischmann apparently later explained they were worried Jones might patent similar heat-related findings, even if Jones was focused more on neutron detection. It was about staking their claim.
Wow. So this anecdote, it perfectly illustrates Heesen's argument, doesn't it? It's a clear case where the pressure for credit, for priority over a competitor, directly led to publishing research that was, well, ultimately deemed irreproducible.
Exactly. It wasn't just some random error. It seems structurally driven by that competitive reward system. This is the rushing into print Heesen talks about.
Okay, so Heesen doesn't just tell the story. He formalizes this with a model, right? A rational choice model.
Yes, he does. He builds a model based on the assumption that scientists, rationally, aim to maximize their credit per unit time. It sounds a bit cynical, maybe, but it's a standard assumption in modeling science. All else being equal, getting credit faster is better for your career. More publications, more citations, sooner.
Right. Faster publication equals more credit accumulation over time.
That's the core assumption.
And if that's your goal, maximizing credit per unit time, I can immediately see the trade-off. Spending more time makes your work more likely to be reproducible.
Let's call that probability a P. More time increases P.
Right. But more time also means slower publication. Let's call the publication rate lambda. So increasing P means decreasing lambda.
Exactly. That's the fundamental tension. Speed versus reproducibility. It maps perfectly onto Fleischmann and Pons saying they wanted 18 more months more time for higher P, but it would have meant a lower lambda, a longer wait for credit.
Okay, so that's the scientist's dilemma. Where does peer review fit into this model? It's supposed to be the gatekeeper, right?
It is, but Heesen includes imperfect peer review as a key ingredient. Peer review tries to screen for accuracy and tries to estimate that future reproducibility P, but it's not perfect. It makes mistakes. Specifically, it can produce false positives. That's when erroneous or irreproducible results do get accepted and published. Think of the initial cold fusion paper. Let's call the false positive rate alpha, and alpha is greater than 0.
Okay, so bad stuff gets through sometimes.
Yes, and conversely, peer review can also produce false negatives. That's when accurate, reproducible results get rejected. Let's call the acceptance rate for good papers beta, and beta is less than 1, meaning some good stuff gets blocked.
Got it. So peer review isn't a perfect filter.
Not at all. And crucially, the model highlights that the existence of false positives, alpha 0, the fact that flawed work can get published and receive credit, is a major driver of this rushing into print problem.
Okay. But let's say a result does get published, and later it turns out to be wrong, irreproducible. Does the scientist get any credit for it? You mentioned this earlier.
Yeah, that's a really important point in the model. Heesen notes that the credit for erroneous results, let's call it C, isn't necessarily zero. Research that's eventually proven wrong or irreproducible can still rack up citations, influence discussions, and, contribute to a scientist's reputation, at least for a time.
Like you mentioned Priestley and phlogiston wrong theory, but still historically significant.
Exactly. Or think of more modern examples, like studies that get retracted but have already been cited hundreds of times. That credit doesn't just vanish overnight. So C can be greater than zero.
Okay, this raises a really important distinction then between the credit a scientist gets, C for accurate, C for erroneous, and the actual social value of the work, C for accurate, C for erroneous.
Precisely. Social value represents the real contribution to scientific knowledge and ultimately to society. Accurate results clearly contribute positively, but erroneous results, even if they get some credit, can actually have negative social value. They can mislead other researchers, waste time and resources, maybe even harm people if it's, say, a flawed medical study.
Right. So an inaccurate paper might get lots of citations, I see, but actually hold back progress, negative in.
That's the potential disconnect.
Yeah.
And this leads to Heesen's critical assumption, the linchpin for his rushing into print theorem. He assumes that generally the credit for accurate results is roughly proportional to their social value. That seems reasonable.
Good science gets rewarded appropriately.
But, and this is the crucial part, he assumes the social value of erroneous results is less than the credit typically given for them. So they say.
So the reward you get for publishing something wrong is often greater than its actual benefit or less than its actual harm to science and society.
Exactly. There's an inflation of credit for erroneous work relative to its true value.
And that leads to the theorem.
Yes. That leads to Heesen's rushing into print theorem. Given all these conditions we've discussed, the speed or producibility trade-off, credit rewards for publication, imperfect peer review allowing false positives, and this crucial gap where Heesen's model predicts that a rational, credit-maximizing scientist will choose a target level of reproducibility for their work. Let's call it PC for credit optimal. That is lower than the level of reproducibility that would be socially optimal, PV for value optimal.
Wow. So the system itself incentivizes scientists to aim for less reproducible work than would be best for science and society overall.
That's the stark conclusion of the theorem. The incentives are misaligned.
And Heesen complicates it even further, right? Adding a third dimension, impact.
He does. He introduces a more complex three-way trade-off: speed, reproducibility, and impact. Scientists aren't just choosing speed versus reproducibility, they're also considering the potential impact of their work. He talks about different types, maybe impact seekers, drawn to higher risk, potentially high-reward research like cold fusion was supposed to be.
Versus maybe safety seekers who prefer to make smaller, guaranteed correct, quicker contributions. Steady progress.
Right. But what's really fascinating is that the models suggest these aren't just like personality preferences. They might reflect differences in a scientist's underlying aptitude, the inherent shape of their individual speed or producibility impact function.
What do you mean?
Meaning the model implies that high-impact, potentially transformative research might be inherently less likely to be highly reproducible, especially in its early stages. It's just riskier by nature.
That makes intuitive sense. Big swings are more likely to miss.
Exactly. And this observation, Heesen argues, actually provides a theoretical justification for practices we already see, like at the NSF or NIH, where grant proposals are often evaluated on transformative potential separately from their likelihood to succeed.
So they implicitly recognize that the most groundbreaking ideas might not look super solid or reproducible right at the start.
Precisely. They understand this tension between aiming high and having immediate certainty.
Okay, so let's pull this all together. The core problem Heesen identifies isn't just one thing. It's the interaction of these three key ingredients, right? 1, the inherent trade-off between speed, reproducibility, and impact. 2, the fact that science rewards publication credit. 3, the reality of imperfect peer review that lets some flawed work through.
Exactly. Those three things interacting create the systemic misalignment, a structure that pushing towards results that are less reproducible than would be socially optimal. And again, it's crucial to see this isn't necessarily about scientists being unethical or sloppy. It's about rational actors responding to the incentives embedded in the system they work within.
Right, it's systemic.
Yeah.
So what about solutions? If this is baked into the system, can we even fix it?
Well, Heesen discusses potential avenues, building on the model. One obvious target is peer review. Can we make it better? Specifically, can we reduce the false positive rate, alpha? Get better at screening out irreproducible work before publication.
Sounds good in theory.
But predicting future reproducibility perfectly is, well, likely impossible. And there's a danger. If you make peer review too conservative to avoid false positives, you might increase false negatives, beta.
Meaning you might reject more genuinely good, maybe slightly risky, but ultimately correct research.
Exactly. And that could actually lower the overall social value generated by science. So it's a delicate balance.
Okay, what else? Can we change the credit side?
That's another angle. Try to reduce the credit given for irreproducible results. Make it closer to its actual, often low or negative social value. How? Well, maybe by increasing awareness of research that's been refuted or retracted, making sure hiring committees, promotion panels, grant reviewers are aware of this, not just looking at raw citation counts, which might include citations criticizing the work.
So making the reputation system more accurate, more reflective of long-term validity.
Something like that. Then there's a third idea, proposed by others too. Maybe limit the number of publications scientists can put out per unit time.
Like a cap on papers per year, how would that help?
The thinking is, if you can't maximize credit just by publishing more, you might shift your strategy to publishing better, more reproducible work. Prioritize quality over quantity.
Interesting. But sounds tricky to implement fairly.
Extremely tricky. As Heesen notes, different scientists have different aptitudes and speeds. A single cap might penalize highly productive researchers unfairly or not constrain slower ones enough. Finding the just right level seems very difficult.
So it sounds like while those other biases, publication, novelty, checking bias, might have clearer potential fixes, like rewarding replications, this rushing into print phenomenon is, well, deeper, more tangled up in the fundamental reward structure, harder to surgically fix.
That seems to be the implication. It's a more fundamental consequence of how we've structured scientific competition and reward.
Okay, given all this modeling and theory, let's circle back to Fleischmann and Pons one last time. How should we reevaluate their decision now? It's been so heavily criticized, right? Called premature, a fiasco.
Yes, it's been much maligned, as Heesen puts it. But his analysis suggests maybe we should be a bit more nuanced. From their perspective, at the time, given the information they had and the incentives they faced, was their decision completely irrational? Maybe not.
How so?
Well, first, the model shows that with imperfect peer review, alpha 0, it can be rational for a credit-maximizing scientist to publish something even before they're fully certain about its reproducibility. The system allows, even rewards, some risk-taking.
Okay, the possibility of getting credit for something potentially wrong exists.
Second, Heesen's point about impact seekers and aptitude suggests that scientists pursuing really high-impact, potentially transformative research, which cold fusion absolutely promised to be, maybe, should be given a bit more leeway for work that seems less certain initially.
Because the potential payoff is so huge, it justifies a higher risk of failure or irreproducibility early on.
Perhaps. So Fleischmann and Pons were weighing this immense potential reward, the glory of solving the world's energy problems, against the high risk of failure and the very real, immediate risk of being scooped by Jones.
Right. It was a high-stakes gamble under pressure.
Exactly. So while in hindsight, the outcome was undeniably a fiasco for them and for the field, Heesen's model suggests their decision wasn't necessarily irrational given the systemic context. Maybe it was more a case of extremely bad luck in how the scientific dice roll played out, rather than just pure foolishness on their part.
That's a really interesting counterintuitive way to look back at it. So wrapping up this deep dive then, we've explored how the scientific system's reward structure, particularly this drive for credit and impact, interacting with imperfect peer review, creates this powerful systemic incentive to, well, rush into print.
Yeah, and this can unfortunately lead to results that aren't as reproducible as we'd ideally want, or as would be best for scientific progress overall.
And the key takeaway really is that this isn't necessarily about blaming individual scientists for being sloppy or dishonest, but understanding a deeper systemic misalignment within science itself.
Absolutely. It's about seeing the complex interplay of incentives and pressures that shape how science actually gets done. It's not about casting blame, it's about understanding the system.
So what does this all mean for you, our listener, as you navigate the flood of new information, scientific claims, headlines? Well, this deep dive hopefully encourages you to look beyond just the exciting claims or the fact something got published. Maybe consider the underlying pressures, the incentives, the context that shapes how that science was conducted and shared. It invites, I think, a more sophisticated critical engagement with scientific findings.
And maybe here's a final provocative thought to leave you with. Building on that idea of high-impact research being inherently riskier. If potentially transformative science is often less reproducible in its very early stages, should we as a society and should scientific institutions think about new ways to value and fund that kind of exploration? Could we create perhaps more protected spaces for really early stage high risk ideas, freeing them slightly from those immediate intense pressures of publication and priority disputes? Something to think about.
Definitely something to mull over. How do we nurture breakthroughs without demanding immediate, perfect reproducibility? Thank you for joining us on this deep dive into the fascinating and complex world of scientific incentives and reproducibility. We'll get you next time.